Here is a frozen comet, and this is probably how you should picture most of them, as frozen icy chunks. And so we would call this the nucleus of the comet. It's going to be mostly ices, so think water, methane, and ammonia ice, but there will be some rock and some metal in there. If this comet gets close enough to the sun, so maybe about Earth's orbit or closer, the sunlight will start to melt the ices, and some of the material will be able to escape in jets. So this is a comet that is getting close enough to the sun to start melting. If we were to take this comet and zoom out a little bit, those gases that are escaping would fill out a fuzzy little ball, and we would call that the coma. So the nucleus, the actual chunk of material, is very small and is hidden down here, deep down in the coma. So some people like to think of the coma as a huge, dusty atmosphere around that melting nucleus. An atmosphere might lead you to think that it's denser than it actually is. It's going to be practically the vacuum of space. And a lot of that material is not going to be held onto that nucleus with gravity. It's going to be able to get blown away by the solar wind into a tail of the comet. Right. If it was far away from the sun, it wouldn't have any coma or tails. It would just be a nucleus, the frozen chunk. But as it gets closer to the sun, the jets will form, the coma will form, and some of that material will start to be pushed back into a tail. As the nucleus melts, different ingredients are going to be able to escape, and they're going to do different things. So the dust that exists in the coma is going to be weakly pushed by sunlight. So your dust tail might be here, all right? Kind of pointed back along where the comet came from, but also pushed away from the sun by the sunlight. Okay. The vapors that are in the coma are going to be exposed to ultraviolet light. So the gases are going to turn into a plasma. They're going to get ionized. Once your gas gets charged, it's going to be easily pushed by the charged solar wind. So the plasma is going to get pushed directly away from the sun into a different tail. Okay? Directly away from the sun, directly away from the sun. Okay? Another thing that gets freed up while the nucleus is melting are little pebbles, little particles. So think little chunks of rock and metal. Those are so massive that they're not going to really be pushed by sunlight at all. They're not going to really be pushed by the solar wind at all. They're not charged. Okay? So they basically just litter the comet's orbit. Here's a picture of two different tails. Here's the plasma tail. Here's the dust tail. So I can tell you where the sun is. Follow the plasma tail. It points at the sun, so the sun's over here. Okay? And since the dust tail lags behind a little bit, I can tell that the comet came from this direction. All right, so let's go back to those particles that the comet dropped. So in this figure, we've got Earth's orbit and the orbit of a comet. And you can see that just by the geometry, they overlap in one specific spot. Now, the Earth and the comet never hit. Right? They were in different parts of the orbit at different times. But now that this comet has littered its orbit with little pebbles, Earth is going to come back around and drive through those pebbles, and that's going to make a meteor shower. So here's an animation. Here's the comet with its plasma tail going around the sun. Many comets have very elliptical orbits. We'll zoom in along the path, and we'll find icy chunks that were left behind. Earth's orbit, in this case, intersects with this comet orbit in one spot. Right there. and we intersect the orbit of the comet, Earth drives into these particles, and so they all appear to be coming from the same spot on the sky. Okay? And in exactly one more year, Earth will be in the same spot again, orbiting through it again. So meteor showers repeat every year. Some years are better than other years. Earth might hit a dense patch of particles and we'll have a much better meteor shower. So if you were sitting outside watching this, you'd see pebble after pebble hitting Earth's atmosphere, but coming from the same direction. So they appear to radiate from one spot. And these meteor showers are going to be named after the constellation where these meteors are going to be coming from. You know, if you were sitting out watching one of these, you might see a handful of meteors an hour. This time-lapse picture makes it seem much more frequent than you would actually see with your human eyes. In your textbook is a list of all of the main meteor showers and the dates that they happen on. Right, so before I go camping, I print off a sky map so I can look at the constellations and the planets that are up, but I'll also check to see if there's a meteor shower while I'm out in the country. Right. You've got two main regions where comets will come from. So let's look at the solar system real quick. Here's the sun, the inner planets, and the asteroid belt, but let's zoom out. So all the inner planets are down in here. Then you have the outer planets. And here's the Kuiper belt. It's basically a collection of objects that were left over from Jovian formation. This red orbit is Pluto. So Pluto is a Kuiper belt object. We have found many other objects out in the Kuiper belt with Pluto, some of them comparable to Pluto's size. But if we zoom out even further, so Pluto would be down in here, we think that there are a huge number of comet-like objects that are out here in what we call the Oort cloud. Now this Oort cloud picture right here is just art. We haven't taken a picture of it. These dots of these comet locations are completely not to scale. Right? It's going to be almost completely empty space with a chunk here or a chunk there. Right? So these are pieces that got ejected out of our solar system. They got too close to Jupiter, got flung out. So some of these objects out in the Oort cloud are probably never coming back. So let's list off some of the other things that are out in the Kuiper belt with Pluto. Right? So we imagine thousands and thousands and thousands of smallish comets, 20 miles across, 30 miles across. But we have also found some bigger objects. So we've got Pluto. It has 5 moons. The biggest one is called Charon. There's an object called Haumea with a couple of moons. Makemake, Varuna, Ixion, Orcus, Quaoar, Sedna, Eris, and 2002 TC302. Up until 2015, this was the best picture we had of Pluto and its moons. All right, these objects are really far away. They don't get much sunlight. They don't reflect much sunlight. And this was the best that we've done. All right, the New Horizons probe swung by in 2015 and returned a lot of gorgeous pictures. It is still returning a lot of its data slowly. Okay. We found lots of really cool stuff. The surface of Pluto is mostly like methane ice and water ice, and some of it is in really huge mountains. Some of it is in icy plains. We've found very few craters on Pluto's surface, so that implies that its surface is still active geologically, which was really surprising. We would have expected Pluto to have become geologically dead a long time ago. Oh, maybe it's got an inner heat source that we're not aware of. Maybe because it's mostly made of ice, it's easier to deform and erase its craters. Right? And one of the most surprising things to me was to find out that Pluto has a very thin atmosphere of nitrogen. Earth's atmosphere is mostly nitrogen. But because of Pluto's very weak gravity, it is leaking that atmosphere to space. The solar wind is pushing it off, almost like a comet tail. Here's a picture of Charon from the New Horizons probe. It has some more craters than Pluto, but still fewer than we would have expected. Charon has a reddish polar cap, and the best way that we can explain a reddish polar cap is to think that the methane has been exposed to ultraviolet light and has been changed into more complex organic molecules. Organic molecules doesn't mean life, it just means hydrogen and carbon chains. Right? Charon also has cliffs that could put the Grand Canyon to shame, 600 miles long and 5 miles deep. So we had found all of these objects out in the Kuiper Belt that are comparable to Pluto's size, Eris, Sedna, Haumea. So every year, as we discover more of these, should we rewrite the textbooks? This year we have 20 planets. Next year we've got 22 planets. Or should we demote Pluto and not call it a planet? So in 2006, the International Astronomical Unit voted to demote Pluto. So now Pluto is a dwarf planet. So as of 2006, a planet has to do all three of these things: orbit the sun, which Pluto does, is spherical, which Pluto is, and has had enough gravity to have cleared out its orbit from debris. And Pluto lives in the Kuiper Belt. It's in a debris field. So Pluto got demoted because we added number 3. So a dwarf planet is going to only do number 1 and 2. So Pluto is now called a dwarf planet. And a minor planet is only going to be number 1. So now Pluto has its own category along with Eris and Sedna and Haumea. I would point out that there is one asteroid that is also spherical. So Ceres, there is an asteroid in the asteroid belt that is a dwarf planet. And all of the other asteroids and comets are in the minor planet category. So if you wanted to look up details about all of the asteroids that we know of or all the comets that we know of, you would look for the minor planet database.